Andy, I'll just let you take it from here.
Okay, thanks, Raymond. I'm going to give it one more minute. We'll start at 3 after. For those that are just joining, we will be doing a Q&A session. So if you do have questions during the session, you can type those into the Q&A section, and we'll work on getting to those questions and answers at the end, and then respond by email afterwards as well. Okay, we're at 12:03. Let's go ahead and get started. I'm Andy Mutziger with the San Luis Obispo County Air Pollution Control District, and I'd like to welcome you all to today's webinar, where we will be providing preliminary results for a research study that compares the emissions and carbon sequestration potential for 3 small-scale in-forest burn methods. I was a project manager and will provide some background before turning it over to our project team. This slide shows the official title for the research study and the logos for the study partners. The study was funded by the California Climate Investments through the CAL FIRE Wood Products and Bioenergy Grant. This study included both field and lab testing. I'd like to introduce the study's team. Beyond myself as the project manager, we have Raymond Baltar with the Sonoma Ecology Center and the Sonoma Biochar Institute. We've got Karen Youngblood with the Redwood Forest Foundation and the Usal Redwood Forest Company. Stephen Baker is a chemist with the U.S. Forest Service's Missoula Fire Science Laboratory. And Jim Almanet is a soil chemist with Washington State University, working with the DOE's Pacific Northwest National Laboratory. The idea for this study came from a 2019 class and field training on conservation burning that was promoted by the Sonoma Ecology Center as a better way to burn. Some critical differences between conservation and traditional open pile burning include a cleaner, more airy pile construction and lighting the pile from the top instead of from the bottom. From our air district's perspective, we respond to a lot of smoky burn complaints, and conservation burn shows promise for minimizing smoke impacts. Other key differences for conservation burns versus traditional pile burning is the management of the pile to preserve as much carbon as possible within the production of coals. Those coals are then quenched with water, saving the remaining carbon as biochar. With conservation burns, we qualitatively observe less smoke, less combustion, and biochar production. But if we want to shift policies to support burn methods that seem better qualitatively, we need quantitative proof. One thing that we do understand is the durability of the produced biochar. Our air district supports this sequestered carbon as CEQA mitigation for new land use development that exceed greenhouse gas thresholds of significance. Here's a summary of the 6 stated goals for this research study. To quantify the potential emission reductions from conservation and biochar kiln burns relative to traditional open pile burns. To document produced biochar quantity and quality, and to conduct life cycle assessments for the study's test burn methods and 7 other woody biomass elimination methods. For the 35 air districts in California, we want to identify potential burn permit needs and permitting differences for the kiln burn devices, and publish results through a peer review study. And then finally, to provide outreach and educational materials about the results, including today's webinar. From the field portion of the study, this slide shows examples of us starting each of the 3 test burn methods. On the left is the bottom lit traditional pile burn. In the middle is a top lit conservation burn. And on the right is the top lit biochar kiln. The specific kiln the study tested was the Ring of Fire kiln. I'd like to note that for the traditional burn, since our material was well seasoned, that smoky burn phase was pretty short-lived. Here's a quick overview of the replicate testing in the field at the Usal Redwood Forest for the 3 burn methods. From the lab portion of the study, this slide shows examples of us starting each of the 3 test burn methods. We knew going in that we're going to have to scale back the burn size piles for the Missoula Fire Lab's burn chamber. But the necessary reduction meant that the Ring of Fire kiln could not be operated in as designed, and therefore the Ring of Fire kiln data for the lab portion of the study is not included in the results because they simply are not representative. Here's a quick review or overview of the replicate testing at the Missoula Fire Lab for the 3 burn methods. The burn material was well seasoned Doug fir thinnings from the Usal Redwood Forest. We had intended to include some moist replicates, but during the summer when we did this testing, it was impossible for us to drive moisture back into that material. So what we did was we accomplished a second set of laboratory testing for the conservation and traditional burns with that same material that had been exposed to winter moisture this January, and that brought the moisture up to about 24%. Now I'm going to turn over the webinar to Raymond Baltar with the Sonoma Ecology Center and Karen Youngblood with the Usal Redwood Forest Company, and they'll provide some more background on the field portion of the study.
Thanks, Andy. So let's see. As soon as you quit sharing, I will go ahead and share mine. All right. Great. So thank you for coming on, Karen. I just wanted to let everybody know that we do, I'm actually going to go through sort of a slideshow of the actual location and some of our testing protocols, et cetera, that we use there. But I wanted everybody to kind of understand why we as the Ecology Center were interested in this in particular. We've been at training people how to do both conservation burn piles and the kilns since about 2013. And over that time, we've developed a real understanding for how much better these particular techniques are. There's improved pile management. We're conserving carbon in the forest or ag soils, the better use of surplus bioresources. There's the production of place-based biochar, reduction of fire fuels and lower emissions, and then there's this really great opportunity for conservation education. There are other options for some of this material, including local pyrolysis systems that actually produce bioenergy and bio-oil. At the same time, there are biofuels, small milling, mass timber. There's a lot of emerging other uses, but there is still a really important need for, especially in forestry applications, just a better way to burn the material, some of the smaller diameter material. So I'm going to hand it over to Karen, and she's going to talk about the first few slides.
Thanks, Raymond. I'm Karen Youngblood. I'm the Forest Conservation Specialist for Redwood Forest Foundation's Usal Redwood Forest Company. And when Raymond approached us a few years ago about partnering in this project, we were interested for several reasons. As managers of a large timberland tract in Mendocino County, Usal Redwood Forest, we are in the business of growing carbon, sequestering carbon, and burning carbon, most often in the form of burn piles that result from all of our fuel reduction projects, whether it's fire resiliency or timber. So we burn many slash piles every year. Also, Redwood Forest Foundation and Usal Redwood Forest Company are interested in best management practices for reducing carbon emissions, increasing carbon sequestration, clean air, clean water, biodiversity, and overall forest health, while also operating as a timber company for the benefit of our surrounding community. And third, we have an excess of young forest stands that need thinning. So this project was an opportunity to continue one of our meadow restoration projects shown in this slide here, that have encroaching young Douglas fir, the perfect size range needed for the study, 1 to 4 inch diameter. So our role in the study was to provide all the feedstock for both the field and lab burns and host and help with the field burn testing. We used exclusively Douglas fir for both the field burns and the lab burns, and the fir was all procured from the same general site surrounding Dugan's Meadow on Usal Redwood Forest. We worked with the California Conservation Corps to stage the fir, approximately 150 cubic yards in 19 sized piles, approximately 2, 7, 9, and 12 cubic yards on this landing here shown that was immediately below the meadow restoration site, so no vehicle transportation of feedstock was necessary for the field burns. We reserved an additional 100 cubic yards of the same feedstock for the same site to later send to the Missoula Fire Lab for the lab portion of the study. Next slide. Here's a close-up of one of the staged piles. We burned 2 of these piles each day for the field burns for 2 weeks using 3 different methods: the portable kilns, the conservation burn pile lighting on top, and the traditional burn pile lighting on the bottom, which is the technique most of us have been using for decades. And next slide. Prior to burning, I think there's a, yeah, there we go.
Yeah.
Prior to burning, each pile was weighed using this innovative method. Our heavy equipment operator, Kane Finnegan, developed a similar method used for weighing horses. And he and his father, in fact, sewed this canvas tarp and the straps, and we got a hanging scale that we hung from the excavator to weigh each pile prior to burning, as well as weigh the resulting ash or biochar of each pile. And I think at this point, I will pass it back to Raymond, who will describe the rest of the field burn part of the study.
Great, thank you. Appreciate it. So here's just a picture of Emily and Steve, the 2 scientists that were setting up the equipment at the USAL. And it was pretty extensive testing. Steve will go over it later. This is a drone view of the overall kind of setting. You can kind of see the pad that we created here. That was really important because we wanted to be able to scrape up all of the biochar that was produced without blending it in with a lot of soil. So we had a 500-gallon water tender as well. So here's the first pile, just kind of showing you the size difference that from what Andy showed earlier in the lab. We were able to have larger piles, and you kind of see the excavator helping to move the material around. This was a conservation burn pile. We did use a minimal amount of propane to start these, but it was really a small amount. The material was pretty dry, luckily. Sometimes, as anybody knows who does piles, they can be challenging. But in this particular case, we also lit the pile from the downwind side. This is really an important part and feature of conservation burns because the smoke that is generated down below, away from the flame, gets blown up through the flame front and burns it much cleaner. There is always some smoke release, but it is generally much less when you have a conservation burn. So here Steve is maneuvering the sampling probe around. He did that constantly as the wind kind of changed here and changed there, but he was really good about moving it around as needed. Again, here's a kind of a drone view showing a fully engulfed pile and the probe right here. And then here's the measuring station right there. Again, just another shot of a kind of fully engulfed conservation burn pile. This is just showing that Steve did move the equipment around depending on where the wind was blowing. And it was a constant effort to keep that probe in where it was needed. We did process and take readings all the way through the whole process and all the way down to when we were actually quenching the pile. We didn't quench the standard pile burns. We let those burn down as much as we could. Here is kind of what we've been trying to avoid. Again, Andy showed this in the beginning, but usually with a burn that started from the bottom of the pile, the smoke that's produced, up in here in the area that isn't being fully engulfed yet, produces an incredible amount of smoke. And anybody who's lives in wine country or the forest areas sees these plumes all over. As Andy did mention, this did reduce fairly quickly, but it's a feature of not doing conservation burns. Before I go into the kilns, I wanted to talk a little bit about the kilns themselves. We did use the Ring of Fire kiln designed by an engineer named Kelpie Wilson, who's right here. This was not at that site. This was done previously. These were the Cs. But you can see there's a double wall here, and it's critically important to the operation of the kiln. This kind of shows that double wall, again, from the top portion with biochar in it. These kilns are available from wilsonbiochar.com. There are other kilns as well, but we chose to feature this one in particular. I wanted to show you this flow diagram and to emphasize that flame cat kilns are not burn barrels. They are engineered biochar production devices that also reduce emissions. And the cool feature of these kilns are that this air gets sucked up through the two panels that I showed you and go into the fire itself, similar to an air curtain burner, but without the diesel and without the noise and all that. So it kind of acts in that same kind of a way. And here I have a quick video that you can kind of see it. It's not a super good video, but here the heated air is coming up and kind of coming into the flame. And that does help pull the smoke back in, and the preheated air from the gap rises up and kind of creates an envelope. Okay, so here we're just picture loading the kiln. We had 3 or 4 really great crew people up there that would kind of measure everything up. Now, this is an older design kiln. This is what's called a 3-panel kiln. It does generally use slash materials. We try to keep it up to 4, maybe 5 inches in diameter at the most. There is a newer design that Wilson Biochar has done that is a 4-panel design. It's much larger, can take a little bit larger material, and it can create more biochar as well. So here's a picture just of the kind of a fully engulfed kiln here, showing the science being created. Here's just a quick one of Steve moving the probe again. Just a quick little video kind of showing that. At the end, we would extinguish the coals when we were doing the conservation burn or the kiln burn, rake it out. Here, this was a kiln burn showing that there was a much larger amount of biochar produced. These kilns can produce very high quality biochar. We've had it tested by labs, control labs in Watsonville, and can get up to 85, even 9% carbon. And then, as Karen mentioned earlier, we put it into this great sling and weighed it to make sure that we understood how much biochar was created. And I'm going to let Karen take over here again, just kind of explaining the last couple slides.
Yeah, I just want to say that we had a great field team and got some really good work done, produced some interesting emissions data on different methods of building and burning slash piles.
Oops.
And so, yeah, so this picture, it's also our team, but it also includes our heavy equipment operators that were there pretty much every day for the 2 weeks that we did the burning. And finally, I would like to make a plug for all pile burners to consider best management practices for burning burn piles. Piles of wood become great shelter for wildlife. And if you are making and burning burn piles, please keep in mind not only the potential air pollution resulting from your burning method, but the wildlife, particularly slower moving amphibians that may have inhabited your burn pile. If you're not burning in a kiln for the maximum reduction of carbon emissions, lighting piles on the top, as we do for the conservation burn piles, enables wildlife to escape before it's too late. So I will pass it back to Raymond, who will now continue the lab burning part of this study.
Great. So I'm going to actually pass it over to Steve Baker of the U.S. Forest Service Fire Sciences Lab in Missoula, Montana. Go ahead and share screen, Steve.
Okay. We good?
Yeah, great.
Okay. Okay, so we'll go ahead and report on the field emissions results. So you saw that probe that we used. It was an 18-foot probe, and it was actually 3 different tubes that were clamped together to sample different types of emissions, one for PM 2.5, one for gases, and another one for dioxins. So the methods we used, we worked with Andy. He requested that we try to conform with EPA protocol as much as possible. So we did a few modifications of some of our methods to hopefully conform, at least in terms of calibrations and other aspects of EPA methods for some of our measurements. We did continuous measurements of CO, CO2, NOx, black carbon, and PM 2.5. And then we collected smoke in canisters, and we did that at intervals based on what was the rate of consumption of the fuels. So we collected at a lot shorter intervals during the flaming phase when there was a high consumption of fuel, trying to get some estimation of a good weighted fire emission measurement for the whole fire. Because if you just average all the samples together, you really don't get a very good average, because a lot of the fuel is consumed in the first few minutes, and then as it burns down, you get other emissions, but that doesn't represent as much of the total fuel being consumed. We measured PM 2.5 using a MET1 dual E sampler, which is not a regulatory EPA method, but we determined that it would be good in terms of having a real-time measurement of PM 2.5, as well as it has a much lower flow rate, which was ideal in terms of the very high concentrations we were going to get from where our sampling point, which was very near the pile burn, which would load the filters way too fast using a conventional method. Okay, so here are some of the results. So here's a real-time look at CO2. And the first thing that jumps out is that's a very high peak there for over 25,000 ppm of CO2. And that represents the flaming phase. For the traditional piles, the conservation piles were a little lower, and then the kilns was quite a bit lower. And the kilns obviously burn in a different manner than the way the piles do. And you can see as the fire burns down, CO2 concentration decreases. CO, again, during the high consumption phase of the fuel, you get a very large peak in CO, and then it burns down, and CO is usually a function of smoldering emissions. And for these fires, for the traditional, we see a bunch of peaks there of CO, which may be related to the stirring of the fires. Yeah, I'm not sure. And then the, as you can see, the kiln fires were a lot lower in CO than the traditional. Nitrogen oxides. Oxides of nitrogen are usually associated with high efficiency flaming combustion. So again, they peak during the high fuel consumption and then start to go down as the fire transitions from flaming to a mixed phase of smoldering and flaming together. The kiln stayed higher, I think, because the kiln reaches a steady state and doesn't really go to a smoldering phase. It kind of goes to a steady state, more high efficiency kind of phase. Particulate matter follows kind of the same pattern. Black carbon from the aethylometer. Again, black carbon usually is associated with a flaming or a more high efficiency kind of burn. For the kiln, I think that was maybe just one fire versus a number of fires in the three aggregated for the other two fires. So it's maybe not the best representation of the comparison between the three types. But again, you'd expect black carbon to be a little higher for the kiln, which was burning at a little higher efficiency level. Okay, so these are the results from the canister analysis. So these are in concentrations, and from very many studies of wildfire emissions, it's been determined that CO, which is a product of inefficient combustion, correlates very highly with almost every other product of inefficient combustion, VOCs and other hydrocarbons, and that's what we found for this study. And you can see our R-squareds between CO and some of these other hydrocarbons, some C2 and C3 hydrocarbons, was pretty high. Okay, so moving on now, just to define a couple terms that we use a lot in fire emissions work. MCE is the combustion efficiency, and that is the ratio of CO2 to the total carbon. So as fires burn efficiency, almost all of these carbon is released as CO2, and that will result in a very high MCE value of 0.95 or up to 1. And as the fire burns down and becomes less efficient and becomes a mix of smoldering and flaming, or else just flaming, or excuse me, just smoldering, MCE values will go down below 0.9, and for very heavy smoldering can go even as low as 0.7. So that MCE tends to be a very good prediction of a lot of other emissions because it is a measure of combustion efficiency. And then most of our products that we produce from this study are emission factors, which is a very standard unit of measure for wildfire emissions. And those are in units of grams of whatever the specific gas is, like CO2, per kilogram of fuel burned. And that is based on the carbon balance method, which is calculated based on the total carbon emitted the sum of all the carbon gases emitted and the carbon content of the fuel. So here we have the product of all this work is the emission factors for various species. So let's look up to the left-hand side for the emission factors of CO, so we see that the kiln burns had the lowest emission factors for CO. The conservation emission factors for CO were lower than the traditional, but again, the kilns were the lowest, and then as would be expected, the CO2 emission factors for the kilns were the highest, and the conservation were a bit higher than for the traditional. MCE is a ratio of that, so again, the kiln MCEs are higher than the other two. And then for the methane on the lower part there, that was kind of a mix. So generally the methane was a bit lower for the kiln, but we had a couple fires that were much higher than the others. So kind of messed up the ratio a little bit, or the mix a little bit. For non-methane hydrocarbons, which are a sum of all the hydrocarbons except methane, we see it's kind of similar to methane, that the conservation was about the same as the kiln and the traditional. It's hard to really see where there's a lot of difference between them. And then for the PM 2.5, this is based on the filters. So the conservation burns were, I would say, kind of similar to the traditional and the kiln. There wasn't really a really significant difference between the three types. But all of these numbers are very low for emission factors. Generally, emission factors for wildfires range anywhere from 3 to 10, and these were all down in the 1 to 3 range. Okay, so this is a table of, similar to what we just saw, of the emission factors for other compounds, including the ones that we saw in the tables. So just to get some idea of, what kind of levels we see for C3 and C4 compounds. They're generally, of course, much lower than the major compounds, but we did detect quite a few, other emissions for C4s and C5s. Our methodology, we can detect compounds up to C6s. Unfortunately, we're unable to do VOCs like aromatic compounds and other things like that.
Hey, Steve.
Yes.
At the bottom of your slide, there's something that says hide. Would you mind hitting that little button there?
Oh, yeah. Okay, you can see that? Sorry.
Yeah. And if you want to click on your video camera, we'd love to see it too.
Okay. I'm not sure I can right now while I'm doing this. Let's go back. Okay. Okay, so let's look at now the emission factors for the nitrogen compounds that we measured and black carbon. So we were unable to measure all of them, but due to some issues with the atherometer, and the atherometer kind of saturated for some of the fires. But looking at the traditional versus conservation burns, for starters, we see that the they're kind of similar. They're not really that much different, both for the two nitrogen compounds that we measured as well as the black carbon. The kiln values was higher, but that, for NOx, but that was based on just one fire that we were able to measure. But all of these emission factors are very low compared to what we see for wildfires and a few other pile burn studies that have been done before. Okay, so taking in the average of each of these types of burns, we performed an ANOVA test of the averages for the emission factors to see if we could see any significant differences between the three types. And we did. Indeed, we found a significant difference between the three types for CO, CO2, ethane, propane, and MCE, which is, of course, related to CO and CO2. And then going further, performing a multiple range test on those, we found that it was the kilns that were significantly different from all the others, from the other two pile burns, both for all of the species. So there was a significant difference between those types of burns versus the piles. Okay, so looking at, now let's compare our results we've gotten to other studies. And there was a study conducted in 2013 with looking at different types of pile burns in Oregon. And we can see the emission factors for those. And as you can see, the results we got were kind of in the low range for CO and in sort of a mid-range for CO2, and for methane, kind of in the mid-range also. So kind of similar results. PM 2.5, our results were lower than what were measured for those. And then the Fire Lab did a study in 1998 of pile burns in Arizona, more winter type with higher smoldering phase things. And those burns showed much lower MCE values and a lot more smoldering.
Steve, you've got about another minute or two.
Okay, so looking at pile burns versus for the field versus lab size, so at the end of the study, we did 2 each of lab size pile burns just to see if there was some effect from the different sizes of pile burns. So looking at that, we didn't really see a lot of effect. It was kind of a mixed bag. Some were lower and some were higher, depending on the what things we were looking at, CO, CO2, or whatever. So, it's hard to say. And then finally, looking at the dioxin, we got fairly low measurements for dioxins. The samples were sent off to a lab in Minnesota for analysis, and dioxins are expressed in units of TEQs, which are toxicity equivalence, which is based on sort of the toxicity of the specific compound that are looking at. So it's a little different from regular emission factors. But anyway, we only were able to do 3 for the field. We did more for the lab, which I will show later, but the results were low. So in summary, the conservation method had lower emission factors for CO, methane, hydrocarbons, NMHC, and PM 2.4 than the pile burns. And I wanted to, for the lab burns, to quantify the smoldering emissions that were produced after the quenching time, because I think that's where really the advantage in terms of emissions for the conservation burns are, not the actual emissions between the two during the burning phase, but actually what you save in terms of emissions coming later. And the kilns had the lowest emission factors for most of the species that we measured versus the pile burns. Thanks, that's it.
Great. Thank you, Steve. I will go ahead and share my screen if you can get off of yours. Great. Thank you. Let's see. Okay, so let me go to this next slide here. So thank you for that, Steve. That was great. I'm just going to run through really quickly some of the the actual lab and what we did there. I just wanted to quickly say that we did ship up the same material that we used in the USAL. We shipped it up to Missoula in a truck, and that may seem a little crazy, but we really wanted to do apples to apples with both the lab and the field burns. Here's just a kind of a overall map showing where we came from and where we went to. It was actually beautiful Missoula, Montana. If you ever have a chance, you ought to check it out. Here is our leader, grant manager, Andy Mutziger, in front of the lab there. Our crew did saw up and prepare the material because the lab profile was going to have to be smaller for the piles, so we did a fair amount of preparation. We also tried to mimic some of the more moist conditions in a typical forest location. So we wet them outside. There was also a moisture conditioning chamber, which was really awesome at the fire science lab. And so we were able to kind of regulate the temperature and relative humidity. It worked fairly well. It didn't work quite as well as we were hoping, but we were able to raise it a little bit. We did weigh everything just like we did in the USAL. Made sure that everything was about the same weight for the piles. Again, this is kind of showing the setup here and building a pile inside. The piles were significantly smaller. This is kind of showing the whole collection stack and a pile at the bottom that was kind of on rollers, and it had a kind of fire protected base there. And up here at the very top was what was called the crow's nest, where the science folks were and all of their equipment. Again, this is just sort of lighting a conservation burn pile from the top. Here's Cuauhtemoc Villa, who was kind of the lead fire tender in this, looking at a conservation burn. Here's another picture of the overall kind of setup with a fully engulfed pile. Same here. We did let them burn down all the way. And in this case, we did the traditional pile burns last, so we let them burn overnight and collected the emissions that way. We put out the conservation burns and the kilns, which I'll talk about in a minute. We didn't have to use very much water in this particular case, and the lab came prepared to do that. Again, just kind of raking it out, making sure that everything was out. And then we, again, weighed the char from each of the pile burns. Now, we did do kiln burns. We did a series of kiln burns here. However, we did not use the data because we could not get the flame up over the cap, kind of creating what the kilns actually do because the height of the stack was so low. So we did get the data. Steve did. I think he may talk about that or not, but we didn't include it in the study. So unfortunately, we were really hoping to get lab data for this, but it just didn't work out. This is a picture just of the kind of the upstairs setup there in the crow's nest, monitoring equipment. Here's Emily kind of looking at the computer setup. Again, the computer setup. This is where I sat, kind of taking down additional data, weights, and all that. And here's this nice picture of Steve and Emily. And so I am then going to go ahead and give it back to Steve. And Steve is going to talk about the data from the labs. So take it over, Steve.
Okay, we good?
Yep, that looks good.
Okay, good. Okay, so here's the combustion lab way back before there was even an elevator. So this is kind of a diagram of the combustion lab. It's been the site of many emission studies with many cooperators, international and local. So the platform where we do the sampling is 17 meters above the fuel bed. We can control the stack flow as well as the temperature of the chamber. So it takes, the flow that we had going up the stack, that would be about 30 seconds or a little more for the emissions to reach the platform before we actually did the sampling. And we did a background sample of canisters before each burn to get the level of especially CO2 with lots of people in there breathing and such before we did our measurements. The methods were very similar to the field. The big difference was for the PM 2.5, we used a more conventional gravimetric filter system with the 16.7 liter per minute flow rate. And we tried to approximate isokinetic sampling, which we did within 20% of or so. And then we also collected for this study quartz filters to look at the OCEC ratio of the particulate matter. So here's kind of a look at just some of the continuous emission measurements, which are pretty similar to the field. These aren't aggregates like we saw before, except they're for one individual fire. But looking at the CO2 on the left there, you can see the concentrations that we were measuring up on the platform were quite a bit lower than what we got in the field. You see 7,000 for CO2, and we were looking at 25,000 ppm for CO2 in the field. Again, this is a similar kind of display to what you saw for the field for canister. And these are concentrations. And again, these are lower concentrations than we saw. And for whatever reason, which I'm not sure, we didn't get the kind of high R-squared correlations between CO and the hydrocarbon emissions that we saw in the field. Okay, so this is our main product again, is the emission factors for the different species that we measured for the two types of burns. Since we were unable to do the kilns just were way too big for our facility, which was unfortunate that we weren't able to get good measurements for the kilns. So looking at the CO emission factor, conservation emission factors for CO were lower, quite a bit lower for all of the most of all of the fires compared to the traditional pile burning. And for CO2, the mirror image of that would be CO2 emission factors were a bit higher than traditional. And then moving on to methane was kind of a mixed bag again. We saw quite a bit of variation between the different fires for methane emission factors. Yeah, I guess that's all I can say about that. And for non-methane hydrocarbons, kind of the same thing as you saw for methane. We had a few fires that had we had one fire there you can see that had a lot higher value for traditional than the rest of them. And generally the conservation non-methane emission factors were lower, although kind of a mixed bag. And then on the lower level in the middle, the emission factors for PM 2.5, again, a lot of the conservation fires were low, but again, it's hard to say there was a big difference between the two types, other than the fact that these are all quite low emission factors compared to what we measure in wildfires or the few pile burn studies that have been conducted before. And then we have another graph on the right, or a bar graph on the right, for black carbon. And those all are kind of similar. You see some lower values in the traditional, but it's hard to really draw any conclusion that one or the other is higher or lower. Okay, so here's a tabular version of those same emission factors that we saw in the previous graph. And looking at the average for the two types, the first thing that jumps out is that the MCE values for the conservation were a fair bit higher, 0.96 versus 0.93 for the conservation versus the traditional. Although the methane emission factors were pretty similar, but most of the other emission factors that we have displayed for C2 and C3 compounds were lower in the conservation burns than the traditional, which is reflected in the non-methane hydrocarbon sum total NMHC, which you see there, 2.0 versus 1.52. And the PM 2.5 emission factors, which were based on those filter samples that we took, you see 1.83, quite a bit lower than 2.43 for the traditional burns. And then looking at some of the other emission factors here for C4 and C5 compounds, you can see that those were all pretty low in both cases. And then on the same page, we have the NO and NOx emission factors. And the averages for the two burns came out identical, and the NOx was a little bit higher for the traditional, which kind of doesn't totally jive with the fact that it had a lower MCE value. But you can see there's quite a bit of variation, and you see that burn number 20 for NOx had pretty high values, which and a low MCE. It was a little bit of an outlier fire, which kind of affected the average. Okay, so what we were able to collect for these combustion lab fires was quartz filters to look at the OC-EC ratios, OC being organic carbon and EC being elemental carbon. It's, as you can see on the slide, it's a key indicator of combustion conditions. Low OC-EC values indicate efficient combustion, which is, well, that's misspelled, but low flaming fire emissions and diesel emissions. So if you go down to the bottom and look at the averages for F is flaming and S is smoldering. So we collected filters at different phases of some of these fires. And so flaming OC-EC ratios are very low compared to smoldering, which are high. As you can see, for traditional there was 0.84 for flaming and 59.4 for smoldering, and 0.58 for flaming and 25.6 for smoldering. So this is just an indicator of organic compounds that could be secondarily formed as aerosols or other types of things. So as you can see, the conservation burn had lower values for both of flaming and smoldering than the traditional. And so what I wanted to do was try to get some estimate of how much savings in smoldering emissions was gained by the early quenching of these fires in the conservation method versus a traditional pile burning where you just let it burn until it goes out. Unfortunately, most of the fires we did in the traditional method didn't really smolder a long time and didn't have a very heavy smoldering phase. But I got some rough estimation anyway and I think that's a very important advantage of the conservation method over the traditional method is the savings in smoldering emissions, which usually has a lot of the kind of pollutants and hazardous materials and problematic emissions versus conservation where you don't have that because you've quenched the fire early. So for the fires we did, we started measuring at what was the quenching time of all the conservation fires, and I summed up all the emissions that were measured in concentrations and calculating a flow total based on that to get some actual mass of emissions that were saved from the conservation method versus the traditional, which is obviously a very rough method, or very rough estimate. And these numbers are pretty low, but these were very small piles, and the fuel sizes, or the fuel pieces, were pretty small too, and generally bigger fuel pieces tend to smolder a lot longer and produce a lot more smoldering emissions. So anyway, these are the numbers we got from the, what we did.
Okay, one more minute, Steve.
Okay. Yeah, so looking at just the traditional versus conservation method from the two studies, looking, and it seemed like the lab burned a little less efficiently, so we got a higher CO emission factors and a little more emissions, but the main answer is we didn't see a really big difference other than combustion efficiency and propane, which is a little suspect because we use propane to light the fires in the combustion lab. So I think that was what was going on there. And then finally, dioxins. We got a little more dioxins in our samples from the lab results, and there you can see them. And the main message is that a number of studies have been done of dioxins from wildfire emissions, and the numbers just range in a very big range from, as you can see, 1 to 40. So our numbers were generally low, and it's hard to draw any conclusions other than I don't think dioxin emissions are a big factor for the pile burns we did. In summary, our conservation piles were all lower in carbon emissions, except black carbon versus the traditional pile method. And we made some estimation of smoldering emissions based on what we had. But I think with bigger piles and real burning conditions and the number of pile burning that is done, the conservation method could really make a big difference in terms of total emissions from this. That's it.
Great. Thank you, Steve.
Sure.
So go ahead and stop share, and we're going to turn it over to Jim Eminette, Washington State University, Pacific Northwest National Lab.
Okay, I'm going to share here.
Again, we will have some time for questions at the end.
All right. Thank you, everyone, for listening to us talk about this wonderful study. My focus is going to be on reporting some of the biomass and the biochar properties during the experiment. Some emission factors, including a couple new ones that you may never have heard of, and also a preliminary life cycle assessment giving 100-year climate impacts for these different methods. I'm going to break it into two sections, one with the field and then one with the lab, and then we'll go into the LCA. So the biomass in the field is about half 50% carbon, 49.6. And the typical moisture content was about 17%, but there's a fair standard deviation on that. So we'll just keep that in mind as we proceed through. The biochar properties, we collected them for all 14 out of the 15 field burns. And I don't have them summarized in terms of, I'll give you summaries later in terms of absolute averages, but just to give you an idea of what we did collect. Not only did we collect moisture content in the lab, but also carbon content, hydrogen to carbon ratio in the biochar, and then the ash content. And I think one thing you'll notice is the traditional burns have a much higher ash content than the other two biochars. So now this is what I would call the conventional emission factors, and these are very similar to what Steve showed. I mean, it should be very similar. They're based on what he showed. But what we did was we did a different statistical analysis to distinguish between what was significant and what was not. And just here for the major components emitted. And you can see basically the only thing showing under this as being significant are the carbon monoxide values. And I think as Steve mentioned before, carbon monoxide was lower for the flame cap kiln than the traditional and conservation burns. And this is based on the standard emission factor calculation, which is based on the amount of carbon in the atmosphere and the total amount of carbon in the biomass to start with, but it doesn't account for any carbon that might remain in the biomass, i.e. that may have been converted to biochar. So what I show on the next slide is one that's on the basis of instead of dry, this is dry biomass combusted. The next one shows in terms of the biomass processed, how much of the biomass actually was processed. You know, how much you started with so many kilograms of biomass, and what happened to that biomass. So we're setting the bar back so that we're looking at the beginning with the rate of the biomass as opposed to just what was in the atmosphere. And so when you do that, you sharpen your differences a little bit because the flame cap kiln, for example, had the highest amount of biochar produced compared to the other two. Conservation burn was a little bit better than the traditional, but so you see a very clear difference now in terms of total CO2 coming off between the three methods. And then also carbon monoxide again retains its significance. And if you look at the bottom, I just give you an idea of what we're talking about here. The traditional generated about 3% of the original biomass, ended up in the ash at the end of the experiment. For the conservation burn, that was about 7.8%, and for the flame cap kiln, it was about 18%. So that's what we call biochar efficiency. What fraction of the biomass ended up in the biochar? And you can see the inverse of that. You subtract it from 100%. You can see the fraction of biomass that was combusted, 97% for the traditional, 92% for conservation, and about 82% for the flame cap kiln. So what happens is that makes a big difference, particularly when you're comparing the flame cap kiln with the other two, in that the numbers, the emission factors are going to be quite a bit lower for the flame cap kiln because that was never emitted to begin with. We can take in one more step and look at from the standpoint of the biomass carbon processed. And so here we're talking about carbon efficiency. And when we do that, we see that, again, CO2 and carbon monoxide show some differences, particularly for the flame cap kiln. But methane in particular also shows a difference, at least between the conservation burn and the flame cap kiln, where you see there's a significant difference for flame cap kiln methane levels being quite a bit lower than the other two, or than the conservation burn anyway. And looking at the bottom again, now you're seeing biochar carbon efficiency of ranging from about 3% again for traditional, but up to 31% for the flame cap kiln. And the biomass carbon combusted is decreased by those same amounts. So we think when you're looking at this from the standpoint of the biomass, how much of that biomass ended up in the atmosphere, in the case of the flame cap kiln, only about 2/3 of it, a little more than 2/3 of it ended up, of the carbon anyway, and that biomass ended up in the atmosphere. Now, shifting over to the lab, we had, we tried to dry, we had the dry stuff, and then we tried to wet it, and there was very little difference between the two. I mean, significantly, there's no difference, but the average moisture content for all those treatments in the lab was about 13% moisture, which is pretty darn dry, actually. But that was a hot summer in Missoula, what can we say? Again, we collected the same set of biochar properties. We had 22 burns. You can see we're only reporting the traditional and the conservation burns here. So instead of 22, actually, I think we have about 2, 4, 6, 8, 10, 2/3 of as many as we have. So maybe about 15 or so again, but just for traditional conservation burn. As mentioned before, we had problems with getting the kiln. We didn't get a fair. The kiln just did not work in the chamber that we had at the fire lab. So again, going back to lab emission factors, we have conventional numbers, and performing this statistical analysis, we see both CO2 and carbon monoxide are significantly different. They're different from each other. Whereas none of the other parameters of these major set of parameters showed a difference. We go to the biomass processed, where we have biochar efficiency of 3% for the traditional and about 10% for the conservation burn, and it sharpens those differences a little bit more. And then when we go to the biomass carbon processed, again, they're just CO2 and carbon monoxide are the only two that really showed differences, no matter what we had in terms of whichever emission factor we went with. So I want to shift over to the life cycle assessment portion, and I've been using a simple biochar production dynamic life cycle assessment, which is highlighted in the center of this diagram here. We start with the initial biomass properties here, and then we follow the path of carbon through the biochar production process and through a reference biomass pathway, which in this case is what I call immaculate combustion, which basically is a hypothetical that you can instantaneously converted all the carbon in the biomass to carbon dioxide, no emissions of methane, nitrous oxide, or black carbon, no bioenergy produced. There's no permanence of biochar in the biomass carbon, no permanence of that to consider. It's just an idea of a clean way of setting a bar somewhere. But we do include the emissions from biomass harvest and comminution, which is breaking it down into smaller pieces, transport and conversion. Here in this particular study is focusing mainly on the conversion. I did consider some of the fossil emissions during the actual burn, but I'll talk about that later. We look at the biochar produced and the initial carbon stored in that biochar. We look at the bioenergy produced. Of course, in this particular study, there's no bioenergy, so that's always zero. We look at the permanence of the carbon in the soil. I want to just point out quickly, it's a dynamic analysis, and so what we're trying to do is account for the dynamics of the concentrations of greenhouse gases and aerosols in the air after you have a pulse during the production. So at the top, I show the changes in global warming potentials for methane in blue, nitrous oxide in green. They're on the left axis. So you see methane starts around 130 times zero, and by the end of 100 years, it's down around 30 or so. Nitrous oxide starts around 180, comes up to about 300, and then slowly tapers off. And then the third thing I have here is the black carbon aerosol. And this, because it is 100 times more powerful as a greenhouse warming agent, I plotted it using the scale on the right side. And you see global warming potentials that range up to about 35,000 initially, and then down to about 900 or so at the end of 100 years. So you can get the idea that black carbon is an extremely important factor in the climate impact of any combustion process, and that's something we need to measure when we do biochar production as well. At the bottom, I just show that carbon dioxide, there was a pulse of carbon dioxide emitted, and by the end of 100 years, that is decayed because it's taken up by the ocean and other processes. It's decayed down to about 40% or 50% or so of what it started off as. So just we keep that in mind as well. So the whole thing's changing over time, and we have to account for it in order to get an idea of what's going on in the system. So here's a slide that just sort of summarizes the results. I'm going to show you this for one of the burns in the field, the traditional burn, and just sort of walk you through it. I have another 4 slides for the other treatments. I'll show them at the very end if there's time and people want to look at them, but I'll I'll instead focus on the results of these as I'll summarize the results and we can look at that first. So on the left here in the green are the parameters that we work with, and we assume a soil temperature for the stability of the biochar to be about, because that's temperature dependent, depends on the soil temperature as to how long it sticks around for. It's a crude analysis, but it's a valuable one. So I picked the temperature for the Usal Forest, since that's where the biochar or the biomass was harvested. So the annual temperature there is around 13 degrees Celsius. We look at the quality of the biochar, which is the atomic ratio. In this case, for this one, it was about 0.47 hydrogen to carbon. And that's a little on the high side, but it's well within the range of what we consider normal biochar, which is say from 0.1 up to about 0.7. The other thing we consider is the carbon efficiency, which I showed you some data for previously. So in this particular one, it's about 2.5%, meaning that 2.5% of the carbon in the biomass ended up in the char or the ash at the end of the burn. Biomass carbon content's 0.5. This number I just want to mention, this is the CO2 emissions generated primarily by use of the excavator to load and move biochar and move biomass around at the Usal site. When you add this up, it does have an impact overall, but it's just something we need to consider whenever we're doing this work, in that particularly diesel has a very high black carbon emission, depending on whether you have a filter or not on your system. And that's something that is a good way, it's a bad way to generate more emissions than you really want in your overall footprint. So run the cleanest diesel equipment you can is the message. Then we have the next three are biogenic emissions for methane, nitrous oxide, and black carbon. And this one, 2.9 grams per kilogram for methane, 0.079 grams per kilogram for nitrous oxide. Now I should mention the nitrous oxide, there are no data collected for nitrous oxide per se, so we just used a very crude estimate by taking the NOx values and multiplying them by 0.1 on the assumption that nitrous oxide generally is much smaller than NOx, but it's kind of scales with NOx. One of these days we'll get a nitrous oxide analyzer on this system and we'll be able to do some really good numbers. The black carbon emissions, these are based on the values that the ethylometer values that Stephen reported. And then we look at the water content of the biomass. The biochar carbon content in this case is about 43%. But these last 6 or so are really not incorporated because these are mainly for bioenergy, and we don't have any bioenergy going on. So on the right is a demonstration of how the three, well, let's go to the bottom first. We have this term called climate impact of production over 100 years. And that's equal to the sum of 3 different components: carbon efficiency and soil permanence, production emissions, and bioenergy production. With this study, there's no bioenergy, so that's always 0. So we focus on production emissions, which is the main thing we've been doing in this study, but we also kept track of carbon efficiency and estimated how long the biochar would last in the soil based on the temperature of the soil and the hydrogen and carbon organic atomic ratio. So the results over time are summarized in the upper right, where we have the overall climate impact of production is just this heavy black line. And you see it's well above 0. We're not carbon negative by any stretch of the imagination, but it comes down quickly. Most of this high value is due to the black carbon actually is the main issue, but other things obviously contribute. It's almost identical to the production emissions, which is the dotted red dots. You can barely see them behind the black line. And otherwise, because with this particular burn, there's hardly any biochar created. There's no offset down below that would account for um, carbon efficiency and soil permanence, and there's no bioenergy. So it's basically just this one thing we're measuring in this particular case is the production emissions. When you add these up, you get numbers down here in the highlighted in yellow. And what I do is typically report them in terms of tons of CO2 equivalent per ton of biomass carbon. So in this case, that's about a little more than 2 tons CO2 equivalent per ton of biomass carbon relative to immaculate combustion. I'll show some numbers later that give you an idea if we didn't ratio it to anything, what the absolute carbon emissions would be. They'd be about 1.91 tons of CO2e higher, or that's because immaculate combustion is about 1.91. But just for fun, I also throw in some numbers calculated for the tons of per ton of biochar instead of per ton of biomass carbon. Just a lot of people tend to start with the biochar, they want to know its impact, and you can see the numbers are quite a bit larger, particularly in this case because there wasn't much biochar produced. So the same emissions per ton of biochar were quite a bit higher.
Jim, you got about just a couple minutes.
Okay.
Okay.
So to get some perspective, I basically summarized the LCA results here, and these are the on the left column here are the relative to immaculate combustion, and on the right are the absolute numbers. In other words, after you subtract, you don't ratio it to anything. So these are in terms of the most climate friendly at the top and the least climate friendly at the bottom, and the conservation burn seems to take both slots depending whether they measure it in the field or in the lab. The traditional is a little bit higher than a little bit less, a little bit more climate impact in the field and a little less climate impact in the lab. In the flame cap kiln, we only have it for the field. And we need to remember that we only have one rep for black carbon for that flame cap kiln, which is very unfortunate. We assumed we could catch it up when we got to the lab, and then we found out we couldn't get any lab data. So we just had that one number, and so we just need to remember this is not really a good measure of the black carbon emissions for the flame cap kiln because there just isn't the replication. Also note that the black carbon data in the field was kind of spotty. We only had 6 out of 15 burns that we could use. I mentioned the nitrous oxide being as an estimate, and the fact that we couldn't use the lab experiment. And one last thing, just to compare, how does the numbers I just showed you, how do they compare with those in but done for other processes? And basically, this reddish rectangle gives you an idea of the range. This is subtracting those fossil carbon emissions that occurred during the operation for the field. And rather than just apply them across the board to everybody, if you take them out, they average about 0.5 tons of CO2e. So this whole thing is about 0.5 lower than those numbers I showed you in the previous slide. But the main takeaway is that if you look at the typical numbers like Steve was referring to for a wildfire or a slash pile burn, we're way down below about a third of those. It's quite a bit lower. We're about half the emissions you get if you were to landfill these same materials. And then we're lower than a lot of the higher tech biochar production systems. And, the best you can do might be down around 1 or so. If you've got all the bioenergy and you had emission controls and everything, you might be getting down around there. But we're pretty much about where I expect us to be, somewhere in this range. And so with that, I will stop and we can pause for questions.
Great. Thank you so much, Jim. That was great. I think that we can go a little bit long for those that want to. If need be, we can go till about 1:45. So, Andy, I know you have been, if everybody wants to come back on camera, Andy, you have been answering some questions. Would you like to sort of read them out, or how would you like to do that?
Yeah, I thought maybe we could take some of the open questions first and then get into the questions I answered. We didn't maybe cover everything.
Sounds good.
So, first question that came in that of the open questions is, it's interesting that the PM 2.5 is highest in the kiln. Can either Steve or Jim talk to that? I'm not quite sure if that's with regards to the lab or the field studies. So,
Yeah. Can you hear me? Yeah, I'm not sure about that, other than the fact that the emission factors we got for the pile burns were very low. So we're talking really low emission factors anyway. So the kiln, they were higher than the piles, but they're still very low emission factors compared to most studies of biomass burning.
and that may be a result of the fact that the source material that we had was super dry. Is that your thought?
Yeah, I think so. Yeah, especially for the field burns, it seemed like the piles went to almost total consumption of flaming very quickly. So it kind of confounded the difference between conservation and traditional anyway in terms of the emissions. And also were highly efficient, so had low emission factors for most things compared to a lot of other wildfire emission studies.
And I'll say that one thing too is we did run some moist sample tests as well in January, and those results are not reported here today. So we may have some different answers. Not quite sure yet.
I
And
would,
you want to put up your screen real quick, the one with the emails on it, so in case people
Sure.
have direct questions.
Yeah, I'll do
I
that.
would just answer as well. I saw that the flame cap kiln had lower PM 2.5 emissions than the other two, and that weren't statistically significant, but that's what I reported. So Stephen and I will get together and work out, make sure we're together on this before we proceed further. That's why these are considered very preliminary.
That question was asked before you came in, Jim, and kind of showed your results as well. So
Okay, moving on. Let's see, was there an account for any effect of the kiln funneling smoke toward the probe?
not really. No, I
Okay.
mean, Steve did the best he could, kind of moving it.
Oh, yes, I'm not sure what you mean by that, other than the kiln was probably the easiest to sample because it didn't have this, as much of a flame height. And I think we got good samples from the kiln.
Yeah, good. Okay, next question. What was the maximum diameter of the biomass material used in the trials? And I'm assuming this is for the field. So Raymond or
I think it was around
company.
4 inches. Is that right, Karen? Kind of 4 inches max. Some a little bit larger.
Yeah, that's true. I think we even focused on 3-inch diameter for the maximum, just for saving time to get through 2 piles a day.
Right.
Okay. Then do you have an estimate of how much difference it makes using traditional piles with quenching versus time and work stacking a conservation burn pile? It's quite efficient to simply quench and avoid smoldering stage in a pile and still be able to efficiently stack with an excavator rather than manually.
I can answer that. And Steve may have some comments as well, but my sense is it's not a bad way to go. You have some differences initially, obviously, in the way that the pile starts, but after that, as we've seen, most of the emissions are fairly similar between the two methods. And we had one where we had we didn't follow it all the way. It burned down, but we went ahead and quenched it prematurely, shall I say, instead of letting it just turn to ash for 6 hours or overnight, something like that. And I ended up throwing that out of some of the calculations I did simply because it was not representative of what would have happened in a pile burn where it would go all the way to completion. And in that one, we saw somewhere about halfway between what we would normally get for a traditional burn and what we would normally get for a conservation burn. So there was about half as much carbon still present, and so I think it's not a bad way to go. And I understand some of the practicalities of not having to stack it. It depends on what's more important, really, though, whether you want to avoid the PM 2.5, the smoky stuff early on, or not. That's a consideration, and certainly from an air pollution standpoint, it's worthy of balancing those things out. So it's a question of what's most important here.
Yeah, and I would say too, if you have the opportunity to try and burn the pile from the top down, as opposed to just burn it from the bottom up, that can help minimize that initial smoke impacts. Especially, this study was working with dry material. If we had moist material, that smoky phase may have been much longer. Okay, let's see. Moving on, there's a number of questions here from Kelpie that are probably specific, and I'd like to try and jump into the other questions that we didn't, that I tried to answer. And then since Kelpie has a number of questions, it may be we can try to get to that at the end or follow up with those more specific question answers. Okay, so let's see. Did the Missoula Fire Lab? Let's see, does the Missoula Fire Lab have the largest test equipment, and is the data comparable to Charpalooza results that took place outdoors? So I had answered in that my understanding is that the Fire Lab's the chamber is one of the largest current available systems for measuring burn emissions. And maybe Steve can talk about the comparison between the field testing and Charpalooza testing.
Oh, yeah. Yeah. Well, I was at Charpalooza and did that sampling. And as we found out, the combustion lab wasn't big enough to do a good test of the kiln at all. So they're not comparable. I think it would be, as is often said, more study is needed, but I think a lot more field type testing of the kiln would be worthwhile to get more reps. We only were able to do, what was it, 4 when we did the field study? And I don't know of a facility inside that's big enough to do the kiln. My idea was to make a smaller version, a small version of the kiln to kind of simulate, but I'm not sure if that would be representative of the larger version of the kiln. So yeah, unfortunately, as I say, the combustion lab in Missoula isn't suitable for kiln testing. I think we got good data from the field, and it would have been nice to get even more data from the field, as well as what we did at Charpalooza.
We'd love to do a follow-on study for sure.
Yeah, one of the things we tested Douglas fir. That's just one fuel source. There's certainly harder woods and other woods that we could test too. So a question came in from Frederick, and he was asking about loading the kiln and what about moist material? And I did some responses to that, but one of the questions that I didn't quite get to is it said it looks like it takes 2 personnel to conduct the biochar, the biomass, or to feed the kiln. and what is their daily pay rate? So just kind of understanding a little bit about, what does it cost to do these more maybe more friendly emission reducing friendly biochar producing burns.
Karen, do you want to take that?
Yeah, definitely two people are ideal, I think, for managing a kiln. One person could do it, but that would be a pretty a lot of labor to put on one person, especially for setting up the kiln and the quenching of the biochar at the end. The daily rate for that type of labor, I mean, it just depends on who's doing the job, whether it's volunteers, which is, ideal, to a professional fire worker where, prevailing wage could be something around $35 an hour.
Okay, great. We had Noah was asking some questions about maybe doing smaller conservation burns to help minimize heat impacts to soils. I made some comments to that in there about that. And it does kind of depend on manpower or person power that you have, and resources as to how big of piles you're going to be making and managing. So, but noted that, certainly heat is an impact on soil health. So he's indicating that, maybe a smaller pile could minimize some of those heat impacts to the soil health.
Ideally, there would be a sort of a burn area. Of course, it depends if you're ag, if you're a vineyard or someplace like that, you can have an area near your compost pile where you do the burns over and over. So you're just impacting one area. If you're out in the forest and you have to do a whole bunch of burns, do them on the road if you can. Same with the kilns. Um, but yeah, it definitely can. However, we found that because of quenching the biochar at the end rather than just letting it burn, it impacts the soil less. The conservation burns in the kilns. The kiln does not have a bottom on it, so you just kind of rake it out.
Those are some good advice there. Thank you. Let's see, we had Gordon. He was asking about the recovery of the biochar from the traditional burns. And in fact, I think Jim's slide showed we were catching all the traditional and the conservation and the kiln burn. We were looking at the biochar and ash recovery for all of that. So that is there. Okay, and then Kelpie Wilson, she had said, were emission factors calculated? And I think I mentioned to her in this particular question that I thought that Jim's responses or his slideshow was going to show exactly what she was looking for, and I'm thinking it did. And if there's, I think so we'll try to get back to her other questions and see if we've fully answered her question. And then Scott was asking, you mentioned weighing the biochar after the burn was complete. Did you factor in the total water weight? And yeah, so this was all done. We've certainly had moist materials, but that was dried to get the dry weight carbon. And then lastly, Annie said, thanks for the great work. Do you have technical report for this project that she could read? And one of the things that's happening right now is Jim is in the process of finalizing a peer-reviewed paper that we will be pushing through to some of the Air District folks that work in this space prior to us sending it up to the peer review journal for publication. And my sense, it takes a while for it to go through that process. My thought is that we hopefully see that article published this year, sometime within 2026.
We've got about 3 minutes left.
Okay, going back to Kelpie's questions then. She said, visually, I see more black carbon when fuel is dry, maybe a trade-off between CH4 and black carbon. Any thoughts from the team?
Yes.
Okay.
And Stephen and I have had some conversations about this. And just jump in, Stephen, if I get it wrong. But my impression is that you get more black carbon when you have flame than when you don't, than you do during smoldering, and you get more PM. Although his data seem to suggest you get PM all the time, but you get more PM or non-black carbon PM when it's smoldering, and so there's a trade-off there. And of course, both of those, neither of those is methane, and so there's the question of you can get lower methane from the kiln, but perhaps a little more PM and a little more black carbon. That's the question based on the one number that we have at this point.
Yeah, generally black carbon correlates with flaming, more black carbon with flaming. And if you have a more efficient burning device, you're going to produce a little more black carbon. But I think overall, that's not a bad thing compared to all the other emissions that are reduced by efficient flaming emissions from the kiln.
And when I in the past, when I've tried to estimate black carbon and all I have is a PM 2.5 number, I just applied a 10%, just said, well, it's roughly 10% of PM 2.5, but now I understand that could be, it's really hard to come up with a number because your PM might be going down while your black carbon might be going up, or there's not a they don't go lock and stock and barrel like carbon monoxide and methane are typically. That's a good thing you can do. If you have carbon monoxide numbers, you can probably make an estimate of what your methane numbers might have been. But black carbon is tough, and it's important, but it's very tough to get good numbers, and we'll just have to keep trying.
Okay, well, on that note, I think we're out of time, and we'll try to get to the other questions, Kelpie, either written or some other way. I want to thank everybody for attending, and hope you learned something here. And we're going to continue working on this. More science is obviously needed, but we were very happy and we want to thank CAL FIRE for sure for funding this, and for Andy to, really kind of managing the whole process. And thanks to all the other contributors as well. So thanks, everybody. We appreciate it.
Thank you.